Let's start building up our Grasshopper definition for scaffolding strategy. So first of all, we need to define the positions of the wooden beams or any kind of beams. It might be aluminum, it might be another material as well. Let's get some references from the entrance hall over here. We are copy pasting because we will reference more than one point. So I will give a little bit more information about the site. That here it should be the other way around. Yes. So here is the entrance. We see the elevator structure down the hall, and we have this entrance hall over here, the walls across each other, and there is a passage going to the staircase. Let's reference our points. I will start from this one. And based on this reference point, I will create a list of curves indicating the positions of the scaffold elements, let's say beams. So surface, we have 4 points, and we're inputting the points. So we created the surface based on these 4 points. And now I will indicate the positions, the linear positions for the beams. For that, there is a component called contour. Which takes a surface as a base geometry and a point and direction for that. We just write vector and then construct direction and then the distance inputs. So based on the surface point direction and the distance inputs, this component will calculate curves along the surface towards the direction which is indicated with this vector, and getting a reference. So starting the curves from this side, if I input this point, it will start calculating from that side as well. So and of course that the curves will be created apart from each other, which will based on the distance which is initialized here. So let's create a vector on the x, give it a number slider, and edit this one between floating numbers and between -2 and 2, and then just copy paste this and then reuse it. Doesn't matter, so I'm just over here. Yes. In this case, we are operating the surface located on the plane of XY. So we will be creating curves on that plane. Accordingly, our z component for the vector should be 0. And let's give this as well 0. And then if I say along the x, let's give a distance as well. We should be seeing curves parallel to y-axis and then perpendicular to x-axis. So if I change the distance, let's change this. Let's give this distance as, so then it's 2 apart, but let's make it maybe 20, and yeah, we can play, we can adjust the distance later on. Let's keep it 20 for now. And if I change this one to, let's say, 0.45, the curves are created along this direction. So let's keep it like this for now. Let's see what we've created. Yeah, so let's indicate another set of curves which are horizontally placed. Let's copy, paste this. And then adjust the components accordingly. So I want to create curves parallel to x-axis. For that, I need to define like a So we have created curves which will be indicating the positions of the beams. For that we need more curves like this, right? We need to iterate these curves along the z-axis by using linear array component. So which will take this curve set and then iterate it along the z-axis n times. We should input the curves over here, and now we need to indicate the direction, which is z in our case. And then we should also give this vector a value. Let's give it 30. So we see that these set of curves are iterated 10 times based on the keeping the distance of 30 centimeters. We need to change the direction in order to define the curves inside of the entrance hole. So use a component called negative. Just plug this in here and then change the direction. And I'm organizing these ones. It's always good to organize your work, your definition. So let's name these components. Now we don't forget the parts of our definition. So by right-clicking group, let's name it by using scribble component. Here basically we can create text. So I will write base geometry, which is ceiling that we get from the ceiling. I will decrease the size of the text. So just by clicking on the text, right clicking on the group, selecting add to group, so we name our let's just give names for these curves. These are the, let's name it like diagonal positions or group. Copy paste. Diagonal curves and add this name to the group, and then I will use the same for this one. Maybe we can also use the same distance, so then we can control the distance from one slider. So let's plug this in and then delete this one, and then maybe I will just click on this slider and right click on the group and remove from group. So I would like to address this distance individually, and then I can even group it by itself. So let's say distance between curves. So now it's more understandable than just a bunch of components. So then they have a name now, which indicates what they are doing. So just group this one as well, and then write parallel let's say horizontal curves. You can horizontal curves, you can name it differently as well. So just some keywords that you could understand. Add to group. Yes. So let's keep going. So this is the iteration, this part, and we will use the same iteration for horizontal curves as well. And then I just plug this the set of horizontal curves, and let's check it out what we have. We managed to iterate this set of curves that we created on one surface, and then we iterated those curves along the z-axis. But for the scaffolding structure, we need to also indicate vertical beams as well, and where we should be indicating these vertical beams, probably in the intersections, right? So then our structure will hold itself, will be able to carry itself. So they should be connected to each other along these nodes. For that, let's find out the intersections for these curves. Don't need these iterations for now, so let's drag them a little bit out of the site. But we will be using the initial curves that we've created here. Let's find out the intersection nodes between these two sets of curves. So we need to write intersection, or just okay. For that, we just go here the tab called intersect. I click on that, and then there is a component under physical subgroup called curve to curve intersections. So let's try to directly plug this one set of curve here on the A, and then this one over here. Yeah, it does not really give what I want. I want to see the whole points that these two set of curves are intersecting. But then it instead of that, I've got this, which is much less than I expected. I will just basically, in order to see more clearly, I will just close this previews, and then it will close the preview by right clicking on the surface, just closing the preview over here. So yeah, we are more understanding, then it's more clear to see what's going on. This is happening because of the data structure of these curves. So they are tree, which means that they are listed as tree, which means that the curves are collected into list of lists. We can see it by going to the list item and then just plug this into here. And then even if you're looking at the first element, first item in the list, so over here that it's 0, so we should be seeing only one curve from here or over here, but we are seeing instead the whole list. We can basically check the data, tree data structure by inputting these curves into a panel, and then you see that we have a lot of lists. So let's try to collect all these curves into one list. Let's try to simplify the data structure by basically flattening the tree structure into a single list. Just plug this in and then see that this component will create a single list out of a tree. Just in order to compare the data structure, I will write again a panel and then click this flattened right over here. So you can see that the flattened component basically converts the tree structure over here, converts it into a single list. Just deleting them. And then if I plug this into here, we see now we are able to get the whole intersection. But we did not do the same flattening for this one. And why? Let's try to do that and see what happens. Flatten. Because this component works in a way that it takes a list of elements or one element and compare it to one element. But in this case, we have a set of elements. So when we flatten this one, instead of one element as a whole list, we have items. Therefore, it's not calculating all the intersections, but instead of flattening this data structure, then we should use the whole list as one item. We can see as panel. And then, so basically that this curves that we have given here will be compared against each curve in the list. So, yeah, now we have the intersection positions. I can even do that instead of flattening this one, just plug this in here. So yeah. Yes, now we have the intersection positions. I think if I decrease the number of the curves, we will be able to see it more. So for that, let's let's go to the distance and then change the distance something more, increase the distance. So let's go for 50. Visually it is more clear. So let's, okay, for that, for the intersections, now that we have the intersections, but we would like to define the positions of the vertical beams over here. Basically we can use the same logic that we used for the diagonal and horizontal curves. The array, linear array. So just copy and paste this. Instead of curves, we can plug points. And we are not seeing anything because this preview, the preview is closed. So by right-clicking preview, and then we see that the vertices, the intersection points, are iterated with the same distance that we used for diagonal and horizontal curves. We need to define curves, not the points. So let's write polyline and plug this over here, and let's see what happened. So we see that polyline component does actually give us what we want, but then it generates a warning message saying that insufficient points for a polyline. This happens, we can disregard that warning because we are not creating one polyline. So obviously that this is insufficient enough, that these points you cannot create one polygon. You cannot create one polyline, but this is not what we want anyways. We want to create a list of polylines. By checking that we created the intersections and what we've created basically. So then let's preview this, preview that one as well, and let's see. So we clearly draw the skeleton or define the positions for a non-orthogonal scaffolding structure. So we indicate diagonal beams, we indicate horizontal beams, we as well indicate the vertical beams for the scaffolding. And yeah, let's move on. We don't want to fill the whole entrance hall with this scaffolding structure, but we would like to indicate voids inside of this scaffolding structure.